All right, I'm Paul Brewster from NASA Langley. I'm going to talk a little bit about this mission that we just flew a few months ago, talk about the software on it. Um, so I even have agendas for you. So since for the couple people in the room who don't know what LOFTID is, which is probably most everybody, this is a reentry vehicle that was designed to test a test demonstration of the aeroshell there in the picture. That's a hypersonic inflatable aerodynamics accelerator. It's basically a big inflatable balloon that will slow down the craft on reentry. And the reason why this is really important is because we could have a really big aeroshell that's much bigger than the fairing of a rocket. So when we come down through reentry, we could bring large objects back and not just what would fit inside of a rocket fairing. The one we flew here is about 6 meters in diameter. We have a plan in the future, maybe to fly one the next time we might be doing 12 meters. This project was the first demonstration of this technology in space. We've done a couple others off of sounding rockets, but this is the first time we put one in space and brought it back down again. So we launched it in November from Vandenberg. It was on an Atlas V. We were the secondary payload to JPSS-2. So we just kind of hitched a ride with them. We orbited the Earth, went around the South Pole, somewhere around the Mediterranean Ocean. We separated from the launch vehicle, went around the North Pole, and then we landed in, near Hawaii. The whole flight was 2.5 hours from takeoff to land, splashdown. And we were, out of that 2.5 hours, we were only powered on for about an hour. But I'm here to talk about the software on it. So here's a quick overview of the avionics. I kind of simplified this down, but really I don't care about much of this. I'm here for software. Here's the components on that had custom software on it. We had the mock or the PDSU flight computer. We have an IDR, an EDR, a FOSS, and camera pods. And then of course these are all network devices, and so there's a data switch to network it all together. I'm going to talk about each one of these individually. Just to frame everything, this was just a technology demonstration, so it was a Class D mission. Software was Class C. Of these devices, the PDSU software is basically the main software of the computer. Ran the timeline, turned things on, turned things off, did the pyros, did telemetry. It was sort of the main part of the computer. We had the camera controllers because we had up to 18 cameras on the system. We had a 360-degree view of the aeroshell from the back. There were 12 IR cameras and 6 visual cameras, and we had a camera controller that Marshall did for us to take care of all that data. We had data recorders. That was, of course, to take all that data and save it so that we could look at it later. We had 2 data recorders running. One was the IDR and the other was the EDR. The EDR, we actually launched the SD card out of that to have it land separate from the launch vehicle, from a entry vehicle, so that we could recover it later and have 2 copies of the data recover. And then the FOSS was something that was provided by Armstrong, and that was a fiber optic system to measure the temperatures throughout the back of the aeroshell. So what I did is I chose one thing I wanted to talk about for each one of these 3. Well, I didn't talk about the FOSS much, but for the other 3, I just one little thing I wanted to talk about. So it's kind of 3 mini talks in one. So first, talk about the PDSU. The hardware for it. This was a mock that was the name of the system. We bought that from Northrop Grumman. It's just a modular system that we could put CPU in it. We could put different analog and digital input modules. We could put power modules. We could put things like that into it. It was a PowerPC processor, and it was running the Linksys operating system. I'm going to talk a lot about that because the Linksys is, when they first told me about it, they said it's running Linux. And I go, okay, great, I know Linux. Turns out Linksys is not Linux. It is a separate operating system, not a different code base. It is a real-time operating system, but it is POSIX compliant, which means it looks a lot like Linux because they're all. So it's going to be easy, right? It looks like Linux. And we were running CFS 6.5. That's a little bit old now, but that was what we were running when we started, and I made a lot of changes, so I didn't want to update later. Since it's CFS, here's a typical lollipop. All right, so this is what I wanted to talk about. What I had to do to CFS to get it to run on the LinkSauce. Why it's interesting is because, like I said, this was POSIX, so it should be easy, right? Just slap it on, everything will run. But it didn't. So here's some of the things I learned. Most of it was in the OSAL. Turns out, which is the OS abstraction layer. It turns out, number one, that the signal handling is ambiguous in POSIX. Which thread receives the signal is not well defined. In Linux, it was one thread would receive it. In LinkSauce, a different thread received the signal. So it didn't work because the signaling system, which was how the whole timing of CFS works, didn't work at all. So I had to rewrite this part to map everything onto one thread to receive all the signals. And so if anybody needed to do, any other thread needed to do signaling, they had to send a message over to that thread, say, hey, I need a signal. And that thread would create it and then send it back. And every time it went off, it would have to send it back. That was kind of fun. Number two was because this is a little bit older, pthread did not support recursive mutexes, which was all throughout CFS. So we just added that. I just added that capability into an OS mutex and wrote my own recursive mutex, and that worked fine. The other one, a dynamic object loader, they just use different APIs, so I had to use a different dynamic object loader. And then in the PSP, the shared memory system is actually different as well. There's apparently multiple ways to do shared memory in POSIX, and Linux does one way, LinkSauce does another way, which is called the real-time shared memory. So I just reworked that way. And then, of course, I have to rewrite the PSP to work with this timer thread as well. There were a bunch of minor changes. I'm not going to go through these. These were just library calls that had changed, older library calls, whatever. If you want to look that up later, you can if you ever need to. But just there were a bunch of other changes I needed to make. But after all that, CFS worked quite well on this. We really had no problems with it after that. So that's what I wanted to talk about on the PDSU. So now I want to talk a little about the camera controller software, because this is a lot of fun. The camera controller was divided up into camera pods. Each camera pod was 2 infrared cameras and 1 visual camera, along with a computer to process them. What you see there, that's the cameras and the lenses and everything. Here's what the computer was. We used an AITech A176. This is based off the NVIDIA Jetson TX2. They chose this because of the GPU on it. They wanted to do hardware encoding and decoding. It has an ARM processor, and I can tell you what that ARM processor is. It's a Cortex. It's not my processor anyway. It was running Jetson Linux, and the framework is, we did this just using GStreamer. Remember this, since this was a demonstration and Class D, we were allowed to use this kind of stuff that wasn't really necessarily flight ready. But it worked really well. The GStreamer is just a media platform, media framework, and the idea of the software, it would take the images in, take the video in from the 3 cameras, do all the encoding, decoding, and hardware using the NVIDIA chipset. They record the full resolution out to an onboard storage, and then it would downsample the visual to a 12 megabit data rate. We were trying to limit how much we could send over the network. And then it would also only send 1 hertz the IR video, instead of keeping the full 10 hertz that the IR video was coming in at. So it's pretty simple. It's pretty straightforward. It worked really well. Marshall did a good job with that. And the last one I want to talk about was the data recorder. Now the data recorder, all these devices, the FOSS, the MOC, the camera pods, they're all hooked up to the data switch along with some GSC stuff. And the IDR, EDR are 2 data recorders. So each data recorder is basically a computer and an SD card. The job of the data recorder is to take all that data, save it to disk, because of the way we wanted to do this, we wanted all the data to go through a multicast UDP. You remember I talked about we had a limited bandwidth. So that was with multicast, each device had to only send the data once, and then only the devices that were interested in it would receive it. So that was to limit, that way, otherwise the camera pods would have to send the data to the IDR and to the EDR and to the GSC, which would multiply how many times we sent that data. Then the IDR and EDR were responsible for just simply grabbing that network data. They did nothing with it. All they did was store it. So they didn't try to they didn't try to process it. They didn't even data stamp it really. They just stored it. With the hardware, we use the exact same devices. This came along a little bit later because we didn't originally have this in the system that we needed to do this. So we just grabbed a computer that we already had ready to fly and repurposed it. The difference is the framework. We use libpcap. That's a library that's basically the library that Wireshark is built on. So we kind of did a custom version of Wireshark. What gets interesting is because it's a data recorder, we really wanted to check our data integrity. So we spent an extensive testing to make sure that our data was exactly right. What we found, if you look at this, we kind of have a pipeline here. We have data sources. They go send the data to the switch. That goes to the data recorders, to the threads there who write it. And then we do a post-processing check on it. We found data loss in all 4 areas. Well, 3 areas, and then the 4th area was how we found it. We found the data was not being properly routed at the switch, was not being properly received by the recorder, and was not being written by the recorder. So here's what we did about that. The first one was interesting. The data switch was spec'd out just fine. We said we looked at it all. We said we have 20 megabits of data. We tested the data switch up to 60 megabits of data. Said this switch has plenty of bandwidth. This will work. And then when we did testing, every few minutes we would find dropped packets, and we look it up, and drop packets happen when the data switch is being overwhelmed. And we're trying to figure out why is the data switch being overwhelmed. A little bit closer examination, we found out those multicast packets. Yeah, they were being sent to everybody. They were only supposed to be sent to the devices that were listening for it, but the router didn't care. It just sent it to everybody and said, it's up to you guys to figure out if you want it or not. You guys drop it, I'm gonna send it. So there's a simple answer to that. You turn on Internet Group Management Protocol, and that tells the switch to actually keep track of things. And that solved a lot of the problems, but it didn't solve everything. The other problem we found was we were still getting data drops. And we kept going back and forth saying, we can't be overloading the switch. We're well under what we tested for. And our average bandwidth is just fine. Everything looks just fine. We got into more and more detail until we started looking at it down at about the 10 millisecond level. And we started seeing, remember those IR packets, IR images? They were all synced together because we wanted to take an image at the same time. So we were having 12 IR packets being sent at the exact same time. Well, more or less at the same time, of course. Anytime they happened to line up within about the same 10 millisecond window, they would overload the switch. And the answer was simply to stagger those. But it took us we had to dive down at that level before we realized that the instant bandwidth is not the same as the average bandwidth. Once we did that, then after that, we never had any drops on our data switches. For the data recorder receiving the data, we went through several we went through several software designs on this. We found that the best way to get this to work was to have one thread for every component on the device. And that thread would try to would have its own libpcap filter and would try to pull off that device with a non-blocking call as fast as it can. It would just sit there and loop over as fast as it can until it ran out of data. Once it runs out of data, it sleeps and lets somebody else just sleeps for 0 seconds just to give somebody else a chance to go. And that actually worked best. It wasn't necessarily, I actually didn't think that was going to be the right answer. I was expecting a different answer. We tried other ways. We tried one single thread to cover everything. And that made the libpcap filter so complex that it couldn't keep up with the data coming in, and it would lose data there. We tried doing blocking calls where we did a blocked call, and then that would let all of them go. And we spent so much time bouncing back and forth, I think, in context switches that we didn't actually get anything with that. I tried non-blocking with the timeouts, and that also, and then using the select function, and that kind of did the same thing. The CPU usage went down quite a bit, but we would still drop packets. So it turned out just having each thread go at full speed, non-blocking until it ran out of data was the best way to write that. And then the last one was writing it to the disk. We had a separate thread to write to the SD card. We found to optimize bandwidth, we just sent 10 megabyte chunks to the drive at a time. That optimized the bandwidth. And that was working fine, except for some reason SD cards do this. Every now and then they just pause for like a second or two. I think there's a reason why, but I don't know it. So we had to kind of start buffering up we had a 10 megabyte buffer that we would, once that buffer was full, we would write it. So we just had to add more 10 megabyte buffers. So we did a double buffer and that wasn't enough. So we started 3, 4, 5. We ended up going, I think it was 8 buffers. We had 8 ring buffers going around where we write to it and read and write that way. So to put it all together, this is kind of what it looks like. The data would come into the kernel buffer. That's just the network driver on the kernel. PCAP would pull it off and separate it had 8 filters running for each device, separated out. Then our software would pull it off those buffers and write it to our ring buffers, where we'd have one was receiving while the other was writing. The receive, when it was done receiving, it would kick it off to the right thread. And we'd have about 8 of those going at the same time. So if the SD card slowed down, we would then catch up later. And that worked really well. And the reason why we know it worked well, here's the fun part, was how did we check all of this to make sure we never lost data? What we did was we would run multiple versions at the same time. We'd have the IDR running, the EDR running, even a GSC data recorder simulator running, and they would all be recording the data at the same time. So then all we had to do was check the data afterwards, although this is now gigabytes of data, to check to make sure that they all received the same data. Now, with the caveat that they didn't start at the same time, so data at the beginning and at the end can be different. The process for that was kind of fun. You merge all those 10 megabyte chunks into one big file. You then had to separate those per device because data order was not ensured by our multi-threading system. So you separated those out by device and then wrote a file with the checksum for each data packet. All you had to do after that was just do a diff on the checksums. And if the checksums were the same, then your data was good, ignoring the changes at the beginning and the end. And so that actually gave us pretty good data at the end. So the conclusions is that everything worked. This is the nice thing about this is we had a definite ending to the flight when it splashed down. That picture on the left is the actual separation from the launch vehicle. The picture on the right is an IR image of it splashing down near Hawaii. It worked really well. It was a very successful mission, and I have some great videos if you want to see it, but I didn't keep them here for time's purposes. You can Google them on YouTube probably. And I want to end it with some credits because there was a lot of people at different places working on this. Thanks. Any questions?